Hello everybody and welcome to our webinar today. We are going to talk about acoustics and acoustic metrology. But before we start, I would like to explain some organizational things. On your right side of the webinar tool, you can see a chat. This chat is used so that you can ask us questions. Those questions are anonymous and only me and my colleague can see them and nobody else. So use this opportunity to ask us questions, and we will answer those questions during the webinar. There are also some handouts available for download. Those handouts are directly below the chat. So that's all regarding organizational stuff, and let us start. So today I'm going to be your moderator. My name is Ivica Baresic. I'm sales and business developer for Austria. And I'm joined by my colleague, Raphael Ludwig, know-how expert and application engineer at Devetron. Hello, Raphael.
Good morning. Hi, how are you doing?
I'm fine. How are you?
Perfect so far.
Super.
Let's
Do you
go
want
on.
to tell us something about yourself?
Yes, some brief words maybe. So good morning also from my side. My name is Raphael. I'm a product application engineer for Devetron since approximately 3.5 years. My theoretical background and my knowledge is also acoustics because I studied audio engineering at the Graz University of Technology, and that was one reason why we decided to do this webinar about acoustic metrology today.
Exactly. And it's a pleasure to have you on the show today. And yeah, so let's start. The first two slides are just shortly about Devetron for the audience who, if they don't know who we are. So Devetron has 120 employees and its headquarters is in Graz here in Austria. And we are active with our subsidiaries or partners in more than 25 countries worldwide. With more than 25,000 systems and 400,000 channels sold, we are one of the leading measurement experts on the market. So our portfolio includes a wide band of mobile or general measurement systems to measure nearly all physical values, for example, acoustics and sound. And we have our dedicated mixed signal power analyzers, and we offer calibration accredited if needed, and all necessary services to help you to make a correct measurement. So, but that's enough about Devetron. Let's start with our topic today, acoustic metrology. Raphael, what is the agenda of today?
Yeah. Thank you very much for the introduction. The agenda for today is the following. In the beginning, we will start with a theoretical background of acoustics and about the sound relevant quantities that are always commonly used when you want to describe acoustics and sound waves, and also the propagation of sound waves in a medium like air. After that, we will talk, as we are also a measurement company, and it's always about measuring sound, about the functionality of measurement microphones. And then we will introduce and explain a little bit the so-called decibel engineering unit, what it is, the decibel, and why do we use decibel in acoustics very often. After that, we will talk about the two words frequency weighting and time weighting, about the reason why we need it and why we use it, and how it is used in the practical life and in the signal processing domain. And in the end, we will introduce the two most common measurement quantities, the time-weighted sound pressure level and the energy equivalent sound pressure level. And then we are happy to answer any questions you may have and which may come up during the webinar.
Perfect, perfect. And I'm very excited about the webinar because it's also very new to me, this topic, and I hope to learn something about the theoretical part of acoustic measurements. And yes, let us start with the overview about sound relevant quantities.
I will ask you something during the day and we will see if you also
Okay,
listen
perfect.
carefully to me today.
Okay, nice. Let's do
Yeah.
so.
So let's start with the sound relevant quantities. In the beginning, what is sound in general? There exist two different definitions of sound, an objective one and a subjective one, whereby the objective one says that sound is the physical phenomenon that excites the hearing and triggers tone, sound, and noise sensitivity. Vice versa, the subjective definition is much shorter. It says sound is the sensation conveyed through the sense of hearing. So In brief words, sound is anything you hear. And when we talk about the propagation of sound, we always talk about the so-called sound wave, because the propagation of sound is a waveform when it is transmitted through a medium like normally air, when we talk about acoustics, but for sure also any other medium like water or any other fluid or any other gas can transmit sound. And when we want to describe the sound wave in a mathematical way, we can use the Fourier series, which says that any waveform can be defined as an infinite sum of sine waves with different frequencies. So in other words, when we look at sound waves which only include one single frequency, a typical sine wave, this sound wave can be described in a mathematical way just by the sine function here with a certain frequency fi and with a certain amplitude y. When harmonics are added to the signal additionally, we still have a periodic sound wave. And then when we have the harmonics, we have to add the sum here in front of the sign, whereby I is the harmonical order starting by 1 and increasing with 2, 3, 4, and 5. So it's an integer. And then we can describe any periodic waveform with this term here. And even if we have non-periodic sound waves, for example, like you see it here, like noise or anything else, we still could describe a non-periodic waveform with this formula here. We only have to make the exception that I is no integer here anymore, but that I can have values with decimals, so 1.37 or 1.58, 2 point anything. That's the only exception we have to make, and then we can describe more or less any sound wave or any sound signal with this equation here. When we talk about the propagation of sound in the space, the speed of sound is always the important thing, which describes the time which has to pass until the sound wave has reached from point A to point B. And this time is the so-called speed of sound. The formula behind the speed of sound is this one. I don't want to introduce and explain the formula in detail. I just want to point out one particular thing, and that's the thing which you see here is abbreviated with theta. That's the temperature of the medium that transmits the sound wave. And there you see that the speed of sound is temperature dependent. And in general, you can say the higher the temperature, the faster the speed of sound is. And in general, as a rough hint, the speed of sound at 20 degrees centigrade is approximately 343 meters per second. And in general, when you talk about acoustics and want to do some calculations, 340 meters per second are normally used in acoustics. When we recalculate this in kilometers per hour, we get the maybe better known 1,200 kilometers per hour, which are something like 745 miles per hour. This is the sound barrier, and when a supersonic jet breaks through the sound barrier, so he flies faster than 1,200 kilometers per hour, you hear that commonly known smash. Yes, so that may be a practical approach how to get in touch with the speed of sound. Additionally, when we combine the speed of sound and the frequency, which you see already here, we can calculate a wavelength of the sound wave. In general, when we talk about the human ear can sense frequencies from approximately 20 hertz to 20 kilohertz. We will talk about that in a little bit later in more detail. And when we connect the frequency and the speed of sound, we can calculate the wavelength in meter. And when we talk about acoustics that can be sensed by the human ear, we talk about wavelengths from approximately 1.7 centimeters to 70 meters, which is approximately 670 inch. And now to the maybe most important physical quantity in acoustics, that is the so-called sound pressure. The sound pressure describes the pressure fluctuation of a medium that transmits sounds, and it has the engineering unit Pascal, which can be split up in Newton per square meter. So the sound pressure describes a force per surface, and it can be regarded as the amplitude of the sound wave. And the sound pressure is the physical quantity, which is always measured by an acoustical sensor, so by a microphone. The microphone always measures the sound pressure. And when we go one step further, we will also introduce later on a bit more detail the so-called sound pressure level, which has the engineering unit decibel. And this is the squared sound pressure to respect the signal energy in reference to a reference value. And then we calculate the logarithm and multiply it by 10. And then we get the sound pressure level. And the difference between the sound pressure and the sound pressure level will be introduced and explained later on also a little bit more in detail.
Okay. Before you continue, I already see decibel here, so we are going to talk about decibel and that unit afterwards, more in detail. But do you have any examples regarding wavelength, for example, for a radio wave or a light wave?
Yeah, for example, when we talk about radio waves, we talk about wavelengths from 1 meter to 10 meter approximately.
Mm-hmm.
So this formula may also be also familiar to the participants who have an electrotechnical background, because this equation is exactly the same to calculate also the wavelength of light, for example, with the only exception that when we talk about electrotechnics, we don't use the speed of sound here, but we use the speed of light. And the formula to calculate the wavelength there is exactly the same. And the wavelength of light, for example, is in the range from 380 to 780 nanometers. So very, very small.
Okay, and as you said, sound pressure has the same value as physical pressure. So it is basically the same.
Basically, yes. So the sound pressure is really a force, and it describes the force per square meter. So it is a pressure.
Okay, perfect.
Exactly.
Thank you. Okay.
You're welcome. So I just changed the slide in the meantime. I want to introduce 2 or 3 additional values, and then the theoretical background is finished. Because in acoustics, we always talk about the sound velocity commonly, which is also a velocity, a speed, because it has the engineering meters per second as well. But this must not be mixed up with the speed of sound. The sound velocity instead describes the particle velocity of a medium through which the sound wave propagates. In general, you can imagine that the sound velocity describes the speed of the oxygen particle oscillating from its reference and zero position while the sound pressure is propagated through this medium. So it really describes the particle velocity of the oxygen molecule when it is oscillating. And just to give you a hint and an indication about the quantity, when there is no sound transmitted through oxygen, the reference and the zero velocity, more or less, of a particle of sound is approximately 50 nanometers per second. So very, very, very low. And we talk about velocities in the nanometer per second range here. And additionally, when we combine sound pressure, sound velocity, and also introduce a reference surface, we talk about the sound power. As we are talking really about the physical quantity power, the engineering unit here is again watt. And the sound power describes the energy that is contained in a sound wave. And it is mathematically determined by the following equations. You use the sound pressure and multiply it with the sound velocity, and multiply it also with the surface through which the sound wave is propagating. And there is also commonly used the term sound pressure level, and this is again the logarithmic value of the sound power in relation to a reference value multiplied by 10. There we have the decibel again here as well. and particularly the product of sound pressure and sound velocity is commonly called the so-called sound intensity, which you see it here on the engineering unit, describes a power per surface. So the engineering unit is watt per square meter. And to give you an indication about the difference between sound pressure and sound power, I want to show you and introduce a brief example to you from the thermodynamics. When we talk about thermodynamics, we have normally a radiator in a room which has a certain thermal power or a certain electrical power, which is the root cause why a temperature is in the room, why a certain temperature is in the room. And the power of the radiator, which is responsible and which is causing the temperature in the room, is always the same. It's just depending on the radiator itself, the power of the radiator, but not on any environmental conditions. But the temperature instead is depending very much from the environmental conditions. And in general, you can say that the further you are away from the radiator, the lower the temperature you sense is. And that's the exactly same behavior with the difference of sound power and sound pressure. Because when you have an electrical machine which emits noise, for example, a vacuum cleaner, like you see it here, or it may also be a refrigerator, for example, this device has a certain sound power, which is the root cause why sound is emitted by the device. And the sound power is only depending on the device itself, but not on any environmental condition. But the sound pressure, which is sensed by the ear, is very much depending on the environmental condition. And again, you can say the further you are away from the source, from the electrical device, the lower the sound pressure level will be. So just to give you an indication what the difference between pressure and power is here in the acoustics.
Okay. Yeah. Okay. Just to make sure that I understood. So I'm going to ask also some questions. Sound velocity and sound of speed. So if I got this correctly, sound velocity is like the molecular, like oxygen, how it vibrates or how fast it vibrates, let's say.
Yeah.
And sound of speed is how fast this vibrating molecule is moving towards a person or whatever. Is that correct?
Exactly. So the sound velocity is more or less a stationary velocity of the molecule itself, and the speed of sound is a non-static, the velocity of the sound wave itself. So it's propagating through the medium as well.
Okay. Okay. And do you have any practical examples for the sound power level or something like that?
Yeah, the sound power level is the noise quantity which you always see at electrical devices in the supermarket, for example. When you want to buy a refrigerator or a washing machine, there's always a decibel value stated, and this decibel value is always the sound power level. And for example, for a refrigerator, we have a sound power level of approximately 40 dB typically, and a washing machine may emit a sound or may have a sound power level of 70 to 75 dB, for example.
Oh, thank you. Because as a preparation of today, I have had a look at the sticker on my washing machine, and it had 68, so that's good.
Okay, that's very good, yeah. Do you also know how to use the washing machine? Or is your wife doing the laundry?
Yes, I was living alone during my studying, so I know how to use my washing machine.
Okay, very well.
Don't worry. I don't like it, but I know how to use it, so it's a
yeah, this one was not prepared.
And definitely not. So, but let's continue. So to measure sound and calculate the rest of the values, I guess everybody knows that you need a microphone. And
Yes.
Can you tell us something about how microphones actually work?
Yeah, so occasionally I also have one here, as I have been prepared to your question.
Okay.
Yeah, how do measurement microphones in the acoustical measurement technology work? Basically, you need a transducer which transforms your sound pressure into an electrical quantity, typically in a voltage in the millivolt range. And when we talk about measurement microphones, the most common converter is the IEPE one. IEPE is the abbreviation for Integrated Electronics Piezoelectric, which may also be known as the abbreviation ICP, or in the US area, the abbreviation CCLD is also commonly used for IEPE sensors and IEPE converters. How is this one working? The converter itself is a piezoelectric material, like a quartz, for example. And it is working in the following way. You see it up here. When no force is applied to this converter and to this transducer, the charge is in its zero position and you won't measure a voltage. But as soon as a sound wave hits the transducer, the sound pressure will cause a force, or will be the force, which will force a shift in the deviation of the charge in this material. And this pressure, this charge shift causes a voltage which can be measured and which is proportional to the sound pressure. In general, when we have a look at the block diagram, for example, we have the piezo ceramics, the transducer here, and in the microphone itself, there is an amplifier integrated, which will transform your charge into a voltage signal, and this voltage will be transmitted through the cable. And here on the measurement system side, the AD conversion will take place. And to make sure that this amplifier is working properly, we need an excitation, a constant current excitation normally. And the excitation current to run this amplifier is also integrated here on the measurement system side. And the excitation current is typically in the range from 2 to 20 milliamps, and the excitation current is also transmitted across the signal cable here. And this is a typical microphone from PCB, just to give you an indication how it looks like. The typical signal and cable is a BNC cable, like you see here, the connector. Also this one, this is a bit smaller, has a BNC connector at the back. And the advantage of this IEPE microphones are, for example, the following compared to other transducers. You have a very high, or you can realize a very high dynamic range with IEPE microphones. So on the one hand, you can ensure low noise floor levels of less than 5 dBA. And on the other hand, you can also measure very high sound pressure levels up to 180 dBA. And the characteristics and the behavior across the entire signal and frequency range is very linear. And by using coaxial cables, you can also realize cable lengths up to 100 meters are possible and can be realized.
Okay, so the A in those brackets behind decibel, we are going to talk about this later, because I have a question regarding this too. And question here is, this doesn't look like a microphone I'm used to, or I know from concerts or from singers. So is that the same, or is there any different to those microphones?
No, there are a lot of differences between concert microphones, which you use for public, you use for PAs and during concerts, for singers or for instruments. As I may have been prepared to your questions, I have one with me as well. Oh. This is a typical concert microphone. You see the size is completely different. Because this one has to be in the hand very well, and this one has to influence the sound field at least, or even as few as possible. As few as possible. And concert microphones also use a different type of transducers. They don't have an IEPE transducer, but for example, they have a dynamic transducer, which means that you have a coil which is wrapped around a magnet. And as soon as the sound wave hits the coil, this is the membrane, the coil will start to bend and to move across the magnet. And then you will induce a voltage which is proportional to your sound pressure again.
Okay.
On the other hand, these concert microphones don't have a linear frequency range because it is intended to have some distortions caused by the transducer itself. So this is desired for a concert microphone, that they don't have a linear frequency range. But here, for the measurement technologies, you don't want any distortion of the signal, so the frequency range is very linear. The directional pattern is also different between these two types of microphones. Measurement microphones have an omnidirectional pattern. So no matter from which direction the sound wave hits the microphone, it is always sensed equally loud. So no matter if it's coming from the front or from the back or from the side, it is always sensed with the same sensitivity. But when we talk about measurement concert microphones, we may we may want to filter out sound from certain directions, for example, from the back. When you think about concerts, you don't want to have any distortion from any other instruments beside you, or also not from the monitor speaker, which is in front of the singer, for example. And there you may have so-called cardioid directional patterns, which focus on the sound from the front and neglect the sound from the side and completely filter out the sound from the back.
Okay.
And last but not least, you also see it here on the slide, measurement microphones have an amplifier integrated here, and you measure and your output, the output is a voltage in the millivolt range. But concert microphones don't have an integrated amplifier. They only provide an output voltage in the microvolt range. And so you need a certain and a special amplifier on your AD conversioning side. So this amplifier here needs to be realized on the AD conversion side as well. And this is also the reason why you cannot connect a dynamic microphone from concerts to your measurement amplifier of your measurement system, because the voltage of this microphone is simply too low and cannot be properly interpreted.
Okay.
There are a lot of more differences, but I think these are the most important ones between these three types of microphones.
Thank you. Thank you very much for that explanation. That's awesome. So, but let's go towards decibel. A commonly used engineering unit within acoustics is decibel, and the physical unit we are measuring is Pascal, as we learned it in the previous slides. So, can you tell us how they are connected?
Exactly. You also took the first sentence from my speech. So the typical engineering unit for pressure in general is either Pascal or bar. While Pascal is the engineering unit which you use always for sound pressure, so sound pressure is always stated in Pascal, and bar is normally only used in today when we talk about fluids or about liquids. But when we talk about acoustics and sound pressure, we always use the Pascal. And when we think about the human sense of hearing again, the human ear can sense sound and sound pressure from approximately 20 micropascal up to 200 pascal. So this is an enormous dynamic range across 7 decades. And as the overview may be distracted about this number of decimals when you want to read off the values somewhere, and it may become very confusing, it was decided to introduce the sound pressure level, so the decibel, for a better overview above and across the entire dynamic range. That was the reason why decibel was introduced. And so you can describe the 7 decades from 20 micropascal to 200 pascal in a decibel scale from 0 to 140 dB. And when we have the appendix level somewhere, for example, sound pressure level, sound power level, sound velocity level, we always talk about the engineering unit decibel. So the level appended always implies the engineering unit decibel. And when we go one step further and have a look at the dependency of the human ear in the frequency range and in the sound and on the sound pressure level, I want to briefly talk about this graphic here. So I also already said in the beginning that the human ear can sense sound pressure in the frequency range from 20 hertz to approximately 20 kilohertz. And with increasing age, the upper boundary may decrease. But in general, this is the frequency range which we normally talk about. And the hearing threshold is the minimum sound pressure level that has to hit the ear to so that the human may be able to sense sound as well. And you see here that that the human ear is very sensitive in the area from 1 kilohertz to 5 kilohertz. And when we decrease the frequency, we need more sound pressure to activate the sense of hearing. And also here in the upper frequency range, we need more sound pressure level to stimulate the sense of hearing. And speech, for example, is in the frequency range from 200 hertz to 5 kilohertz approximately, in a sound pressure level from 40 to 70 dB. And music perceptibility has a larger area, which you see here, for example. A very important and very painful limit is the pain limit. This is normally approximately in the area from 120 to 140 dB. This is the limit and the threshold when you really receive pain because the sound pressure level is that loud. But the pity thing hereby is that a damaging of your human ear can be caused by much lower sound pressure levels already. In general, it is said that the sense of hearing from the human can be damaged irreversibly already caused by sound pressure levels in the range of 85 dB when they hit the ear for a longer time. But the problem hereby is that the ear gets damaged long before you receive any pain. And this is the completely opposite to the other human senses, more or less.
That's dangerous, actually.
Absolutely. So just imagine your finger, you bend it, it will hurt, and then it will break. And here it is the complete opposite direction. And that is also one reason why hearing aids are commonly used and are needed by very much people, because you just don't realize it, and you just don't feel it that something gets damaged. And thereby also, again, my hint, please, when you're affected by loud sound pressure levels, always use a hearing aid to not a hearing protection to not damage your ear.
Okay. Mm-hmm.
When we go back to the sound pressure level, that was a bit different, but I just wanted to say it. When we talk about sound pressure level, again, the equation here, you see it again, is the following: that you use the sound pressure and square it to have a relation to the sound energy, and you have a reference value down here. Then you have the Decadian logarithm and the product with 10, and then you have your sound pressure level calculated from your sound pressure. And just to give you an indication about typical sound pressure levels, the hearing threshold, as we just saw here, is approximately 0 dB. And breathing is approximately 10 dB, whispering 20 dB, and the normal conversation is typically in the pressure level range of 50 to 60 dB. And when you walk along an arterial road, for example, you may be affected already by sound pressure levels from 80 to 90 dB. And this reference value down here, the P0, is exactly the hearing threshold. The P0 is always 20 micropascal, also in the relevant standard. When we talk about airborne sound and about airborne sound, the 20 micropascal are always the reference value which is used to determine the sound pressure level from your sound pressure.
Okay.
So far, so clear, I hope.
So just once more, the very important hint, just because your ears doesn't hurt because of the noise that you're hearing, doesn't mean that that's okay. Okay, so use earplugs if they are offered and if they are necessary. Thank you for that hint. That's very nice to know. As I said before, as a preparation of today, I have had a look at my stickers on my washing machine, and there is also like energy, A++. The more plus, the better the consumption of the energy of the washing machine is. And I saw decibel A as well. And I thought like A, B, C, like A is good and C is not so good. So, but I guess that was wrong. So please enlighten me.
Yeah, when we talk about ABC and stuff like that in the acoustics, we always talk about the frequency weighting of sound.
Okay.
And I want to start with the reason why we use or why we have to use frequency weighting in sound. The reason is the following, that the behavior of the human ear is nonlinear in the frequency range. This means that not all frequencies are sensed with equal loudness by the human ear. And to describe this nonlinear characteristics of the human ear, the so-called phone curves, which represent curves of equal loudness, have been introduced to describe these characteristics. And these phone curves are also added in the ISO 226 standard. And you see these phone curves here on this figure. On the x-axis, you have the frequency, and on the y-axis, you have the sound pressure level. And these phone curves, which you see here, now describe the sound pressure level that has to be emitted by a sound source to cause the same loudness feeling on the human ear. So the phone is a psychoacoustics unit which describes the loudness of a signal, and you also see here that they change with increasing sound pressure level. The characteristics of the human ear also changes, and that's the reason why the 100 phone curve looks different than the 20 phone curve, for example. And the cutting point is always here the 1 kilohertz. At 1 kilohertz, the phone curve, the 60 phone curve, for example, is equal to 60 decibel. That's where the sound pressure level matches with the phone. And just to give you an indication how to read this value, I want to show you these 2 points here. When we focus on the 60 phone curve, this means, and this phone curve explains, that when you want to sense a 1 kilohertz node here and a 50 hertz node here, both equally loud with 60 phone. That's the yellow curve here. The 1 kilohertz node must be replayed with 60 dB, and the 50 hertz node must be replayed with 80 dB to cause the same loudness on the human ear. So there's a difference of 20 dB to cause the same perception on the human ear. This may not sound that much, but please always respect that the sound pressure level is a nonlinear quantity because we have a logarithm in the equation. When we recalculate it back in the linear domain for Pascal, the 60 dB equal 200 millipascal and the 80 dB equal 20 millipascal. And there's a factor of 10 in between. So this is an enormous difference to cause the same perception on the human ear. And just as a side note, here between 3 and 4 kilohertz, the sensing and the sensitivity of the human ear is very good. The reason of that is that this here is exactly the resonance frequency of your ear canal. And that's the reason why we can sense sound here in the area from 3 to 4 kilohertz approximately very well. And to respect this characteristics and this nonlinear behavior of the human ear also in the measurement engineering technology of acoustics, the so-called frequency weighting was introduced. To respect these characteristics now, frequency curves shall compensate these characteristics, and 4 different curves have been developed and introduced to also respect different loudness levels. As you saw on the previous slide, the characteristic also changes with different loudnesses in general. And so we have 4 different weighting curves, A, B, C, and D. And the A weighting, which is the green one here, has been introduced for low sound levels up to 30 phone approximately. The blue B curve here for medium sound levels up to 60 phone. The red one for loud sound levels up to 90 phone. And especially for airplane takeoff for very loud sound levels, the DB D curve, the violet one, the pink one, has been introduced as well. And the letter in brackets here always denotes the applied frequency weighting. So when you see dBA, okay, A frequency weighting applied, dBc, C frequency weighting applied. And the relevant standard here for is the IEC 61672 standard. And when we have a quick look into the signal processing, I want to show you how the frequency weighting is applied to your sensor signal. So we have the sensor's input signal here in the time domain, and then an FFT, a Fourier transform, is applied to the signal to get into the frequency domain, and the frequency weighting equals a multiplication of your signal spectrum with a certain frequency weighting, and then this is just a multiplication. After the multiplication, you apply an inverse FFT again, and then you have your frequency weighted input signal in the time domain again. And in nowadays, more or less the A weighting is the most frequently used weighting curve in the real life. The reason for that is the following, that these different frequency curves have been evaluated and determined by tests with persons, with hearing tests, and during these tests, only pure sine waves and sine waves and pure sine wave sounds have been used to determine these curves. And the problem here is the following: the pure sine waves nearly never occur in the real life, but any sound always have an harmonic. And then during the time, it has been seen and it has been pointed out that the A weighting is more or less the only one which makes sense for weighting signals. And the B curve is completely deleted from today's standards. The C weighting is sometimes used to determine peak sound pressure levels, and the D weighting still sometimes for airplane takeoff noise or for airplane noise in general. But in 90 to 95% of the acoustic applications, the A weighting is used in today's life. And this is always intended by the dBA abbreviation there.
And as I know, you did record something very interesting during your home office, and to show the difference between A and Z weighting, I guess, as I'm correctly informed by you.
Yeah, you saw the webinar in German last week, right?
That as well, yeah.
Yeah. I made a quick recording and a short recording of my coffee machine. And there you see when the coffee is made, you see the sound pressure level A weighted in blue and the non-weighted sound pressure level, so the Z level, in red. And you see here that there is also a significant difference when you weight your signals or when you don't weight your signals. The A weighted sound pressure level is approximately 61 dB, and the Z level sound pressure level, the non-weighted Z sound pressure level is 66 dB approximately. And when you keep in mind that sound pressure level increase of 6 dB means a double sound pressure level, there's a huge difference between A-weighted and non-weighted signals. And the reason for the significant difference can be seen here in the spectrum, because the two highest peaks in the spectral domain are here at 300 Hertz and here at 50 Hertz. And these two peaks are filtered out by the A weighting, because the A weighting filters out the frequencies below 1 kilohertz very much. And you also see the characteristics of the curve here in blue. And so the weighting also makes a significant difference and affects really your measurement values. So always state if a frequency weighting was applied or not, because it really matters.
Okay. And of course, it is only coincidence that you used our measurement software Oxygen for this, of course.
For sure, just a coincidence.
Perfect. So we talked now about frequency weighting, but there is also time weighting. Why is it necessary to have two different types of weighting?
Right. So the time weighting is the other weighting type which is commonly used in acoustics. Why do we use time weighting? The time weighting is used to highlight different signal characteristics in the signal trend. In general, when you look at the signal processing path again, the sound pressure level determination consists of a squaring of squaring the signal to have a reference and a relation to the signal energy, and additionally of an exponential weighting. This is the so-called time weighting. And the exponential weighting could, for example, in the signal processing domain be realized with a low-pass filter with a real pole at -1 divided by tau. And the tau is exactly the time weighting constant. In today's life, two different time constants still exist. On the one hand, the fast time weighting with a rise time and fall time of 125 milliseconds, and a slow time weighting with a rise and fall time of 1000 milliseconds. And as I said, you can imagine this as a low-pass filter, or on the other hand, when we have a look at mathematical equations, the time weighting could be applied by the following equation. So you have your actual non-weighted, not time-weighted sample, here the x ln, and you weight it by a weighting factor, and you add the exponentially weighted sample directly prior with another weighting factor multiplied. And the weighting factor G1, which is up here, is exactly an exponential function to the minus t divided by tau, while the tau is again your weighting constant, 125 or 1000 milliseconds, and the capital T describes the time between two samples. And G2 is just 1 minus G1, and this is a mathematical equation which can be used to describe the time weighting as well. And in the past, there was a third time weighting as well, which is now also not contained in the standards anymore. By the way, the relevant standard is the IEC 60651. And this was a time weighting which has a rise time of 35 milliseconds, so very fast, and a different fall time of 1.5 seconds, so very slow. And in the signal processing domain, you could have realized this long fall time, for example, by a peak detector with 1500 milliseconds fall time. And when you think of this equation, you can imagine that when you use impulse, you have to make a difference when your actual sample is louder than the prior sample, the sound pressure is rising, so you have to use the rise time. And when your actual sample is lower than your sample prior, the sound pressure level is decreasing, and then you have to use the fall time, for example, just to make a differentiation between them. And in general, you can say that the longer the time constant, the slower the measurement values change and can be read off easier from a digital display. And the longer the time constant, the less signal fluctuations can be read off, and the more smooth your measurement signal is. Just think, for example, of an old analog sound level meter like you see here from Radio Shack, which had a needle for displaying the sound pressure level. When you use a fast time weighting, the needle is changing very quickly. You see the sound level deviations, but you cannot read off a value that easy. And when you use slow, the needle is changing very slowly. So you don't see the deviation anymore that well, but you can read off easier an absolute value. And when you use impulse, for example, the needle is increasing very quickly. And then when the sound level is disappearing again, it falls off very slowly. And this phenomenon could also be seen when you instantaneously and immediately turn off a sound source, for example. The red one is the fast weighted signal, so it is decreasing very quickly and returning to 0 after 2 seconds, for example, something like that. The slow one is needs very much time, and after 10 seconds, it only decreased by approximately 35 dB. And the impulse one has the longest weighting function here of 1500 milliseconds, so it is decreasing very slowly, and after 10 seconds, only 20 dB decrease can be read off. And vice versa, when you instantaneously turn on a sound source, again, the real value can be read off quicker the slower the time constant is. So the green one is the fast again. It is there very quickly on the real level. The fast weighted signal needs a bit more time, and the slow weighted signal needs a couple of seconds until the true value can be read off here.
Okay.
So far, so good, I hope, where you use the sound, the time weighting.
Yes. Yes. Can you maybe tell us for which kind of measurement do you use, which time weighting, maybe?
That completely depends on your measurement itself. In general, you can say when you want to see the sound deviations and the changes in the time domain very well, you use a short time constant, for example, fast. But when you're only interested in an average value and you not interested into the deviations in detail, you normally use slow, because you can read off the average value more easily from a slow weighted signal than from a fast weighted signal.
Okay. Okay. Yes, I think we should talk about the last two values. And you said it prior to this meeting and to this webinar that they are very important values. And one of them is the time-weighted sound pressure level. Tell us what it is for.
So one of the most important acoustic sound pressure level quantities is the time-weighted sound pressure level. I just added the equation to the slide here. I don't want to talk about this one in detail here, but you see the exponential function here, which represents your time weighting here. So either fast, slow, or impulse. And from the measurement point of view, the time-dependent sound pressure level, the time-weighted sound pressure level represents the time-dependent sound pressure level during a measurement. So you see the sound pressure level changing in time when you calculate the time-weighted sound pressure level. And you can, for example, use this one to determine the minimum or the maximum sound pressure level occurring during one measurement. And from the application point of view, you use and you determine the time-weighted sound pressure level when you want to see the sound pressure level change during the run-up of a rotating machine, for example. So you see, okay, it is running up, the sound pressure level is decreasing, and there is a resonance, for example, or something like this. When you want to see that, you use the time-weighted sound pressure level. And further and additionally on, you can use this parameter, this value, to evaluate the sound pressure level depending on the rotational speed or on the torque, for example, during a run-up. And when you think about noise monitoring applications, you can use the time-weighted sound pressure level when you want to do the time-dependent trend of the sound during a day. For example, think of the noise monitoring on an arterial road. So you see the sound pressure peaks during the rush hour and the minimum sound pressure levels, for example, occurring during the nighttime. And so you want to, when you're interested in the trend during a longer period of the sound pressure level, you use the time-weighted sound pressure level. And the second important value and quantity is the so-called energy equivalent sound pressure level. Again, the formula is the following one. It is not that complex. And the energy equivalent sound pressure level describes, from the measurement point of view, your energetically averaged sound pressure level of one measurement. So you make the measurement, and during the measurement, you average your sound pressure level energetically. And at the end of the measurement, you only have one single value, which is the energy equivalent sound pressure level. And the LAEQ, this is how it is abbreviated, doesn't contain any time information of the sound pressure level. And that's also the reason why it is not time averaged. And from the application point of view, it can be used to determine the time averaged sound pressure level of one entire measurement. And at the end, you only have one single value for comparing. And for comparing, for example, the sound emission of a device on the test at different load steps. For example, you want to compare the sound level at 3000 RPM or at 4000 RPM, you normally use the LAEQ. And last but not least, the LAEQ is always used and prescribed in standards for further processing to the sound power level. So when you determine when you want to know the sound power level, you cannot just measure the sound power level, but you have to do a sound pressure level measurement. And this is where you use the LAEQ and calculate the LAEQ. And the LAEQ is used for further processing to the sound power level. And both parameters and both values are included in the IEC 61672 standard.
Okay.
So much for the...
So, as announced in the webinar's name, we said that we are going to talk about theoretical fundamentals for that measurement and sound measurement. And there was a lot of theory now, of course, but now it looks like I have to be a mathematician to do sound measurements, to be honest. How does Devitron help the people who have to do a measurement now? Can you tell me?
Yeah, sure, absolutely. You don't have to be a mathematical genius at all to do all these determinations. This webinar was mainly to introduce you into the reasons why certain values are calculated and why certain weightings, for example, are applied. When you use a data acquisition software, for example, like Oxygen, you for sure don't have to do all these calculations manually again and again, but there exist certain mathematical libraries and features which do the calculation automatically. Like also this one is included in Oxygen. Just have to go here to the channel list. My microphone here is connected now to the first channel. Just select your microphone signal, press on add, and then you can go to the sound level determination. So just select your ABCD or linear set weighting, your time weighting constant, and your reference value is also included here. And then you can activate or deactivate certain output signals. And then the software does all the calculation for sure. And all the values are included here in the channel list and are automatically calculated and stored to your data file.
Okay, just a question. I see reference value you said is included there as well. Isn't it always the same reference value as in the calculations we saw always the 20? Why is there now a 1 as I can see as well?
The 20 micropascal are always the reference value when we talk about airborne sound. So when the sound wave is transmitted through air. When we talk about waterborne noise, so about the sound propagation in water, for example, for maritime applications, there is a different reference value because the characteristics of the ear is different in water. And there the reference value according to the standards when you use a water-based sound pressure level is 1 micropascal. That's the reason why there is 1 micropascal.
That explains it. Okay. Okay, so we got actually a question by our audience, and it was asked on slide 13 with that analog meter that you had. Is the time delay linear across the frequencies, or does the filter add non-linearities? Does that question make sense to you, or can you answer that?
In general, this is an all-pass filter, so there is, in the ideal case, there is no delay across the frequency range, but the delay is equal and the same across the frequency range.
Okay, perfect. So, Raphael, thank you very much for sharing your know-how on the webinar today, and for free, of course. That's very awesome, and thank you so much. It is always a pleasure to have you on the webinars. To our audience, thank you for listening. If you have any further questions, feel free to contact us, me and my colleagues. Our contact data are available on our homepage or on social media. Please stay after the webinar shortly online for 2-3 questions, because we would like to make our webinar better. So we have 2-3 simple questions to you. If you have further questions for Devitron regarding sound or any other measurement types or our instruments, just contact us. For those colleagues who may be interested in this webinar, we are going to have a webinar tomorrow afternoon as well. So we are going to repeat this webinar, and at the end of the week, this webinar is going to be on YouTube. Thank you so much, and thank you for watching. Stay healthy, and see you next time. Bye-bye.
Thank you. Bye-bye.